Hello, everyone. We are starting an IITT talk, and it is number 34 or 35. We're almost covered all the technical committees, but this one is a special and dear to me with soul structure interaction. I'm going to introduce the great speakers and share my screen. Let me see, where are you guys? Here. All right, we have with us all the way from Japan, presenting the
Mm.
TC207, Professor Hemanta Hazarika, field
Hi.
observations and lesson learned. He's going to tell us all about it. Dynamic soul structure interaction during the earthquake 2024, Noto Peninsula. Then we have Georgia De Sanctis. He's a director and co-founder of North Geotechnics in the UK. Soul structure interaction in practice. I love that. Always marrying practice to theory. And then we have, wait, yes, Ajay Shastri, senior geotech engineer with Jacobs from Texas, Houston, close to my house in Austin. Welcome, talking about the dead man anchored detaining systems, my favorite. And then finally, from Nigeria, we will have a young lecturer, Opeyemi Adetunji, hydrobiochemical alterations of soil properties and implication on soil structure interaction. So exciting having you all from different parts of the world. I'm going to start by giving the floor to Professor Himanta. The floor is yours. I will stop sharing.
Hey, thank you, Mike. Uh, okay. Okay. First of all, I'd like to thank Mike for his initiative in arranging this talk. And also like to uh, say thank you to all the three speakers here for their contribution in today's this IITT. First, as a secretary of this committee, TC207, I'm going to give you a brief introduction on the activities of this TC. We had our first meeting with ISSMGE board on February 6th this year, followed by second meeting with chair, VC, and secretary on April 6th. And we had a third all-member meeting on May 2nd. And today we have June 1, the IITT lecture, and next upcoming meeting on June 17th during Vienna
Let
conference.
me Let me explain to our viewers that this TC has been dormant and it was stopped by the previous board and it was dormant. And now this is a success that during, this term, my presidency, we are reviving it because it's a very important topic of geotechnical engineering. So if you don't see, because some of them have seen the other episodes and comparing the activities of different technical committees. So they understand now this is going full blast, and we're counting on you, Professor.
Okay, thank you. It's a huge responsibility. Yeah, thank you. Thank you, Mike, for following it up. So we have our chair, Victor, from Singapore, and vice chair, Johnny, from Hong Kong, and myself. This is our leadership team. Uh, and our terms of reference, TOR, is already in the ISSMG website, so you can go through it. We have the objective one is the dissemination of the knowledge. Objective two is the guidelines and recommendations. and 3 is to assist the conference, various conference. And number 4, which is very important, is the industry link. These are the terms of references. And about the past activities, the first conference but not a conference actually, it was a workshop. It was in Croatia in 2011. So our present chair, Victor, was there. Then in Paris 2013, when we have the 18th ISSMG conference, we had a workshop. And then in India, Indian Geotechnical Society's annual conference, we had also a workshop on soil structure interaction and retaining walls. And that was in 2015. I also gave a lecture in that workshop. Then the same year, Edinburgh, we had another seminar, and the Indian workshop and the Edinburgh workshop, the papers were published, combined and published, with edited by that time Secretary Michael and Chair Ulitsky, and then next Secretary Professor Chaudhary. And again in India, 2018, in Bangalore, there was another pre-conference workshop on this TC. And in St. Petersburg in 2018, we had an international conference, and that conference proceedings also was published by ISSMGE. And then before COVID, just before COVID, the first Betancourt conference was held, and followed by another one, which was during the COVID, and it was completely online. And as Marc mentioned, that after that, due to passing away of the chairman, this activities were completely stopped, and then again it is fortunately revived again with the initiative by Marc. About the memberships, we have about 80 members, more than 80, which are whom were listed in ISSMG website. But when I send mails to them, about 15 of them has bounced. Probably they are retired or they are no longer in the same office, same emails. So I unfortunately have to remove them and replace those members with young members from various societies. That is what we have decided in the last meeting. We also have 2 task forces, one on technical task force and another is professional task force. Technical one again is divided into 2, one on soil structure interaction and another one on retaining walls, and professional one with academy industry partnership and outreach. So these were the task forces. We just started, and we have some members within each of these tasks. And for the upcoming meeting, we have the meeting on 17 June from 13:45 to 15:45 for 2 hours. This is the 10TT programs. We have about 6-7 lectures by different members and non-members, including
It's on Wednesday,
member.
right?
Yeah, on Wednesday. Yeah, on
I'll try
room
to see if I can
133.
sneak in.
Yes, please do come. Yeah. So we have also members from TC204 and 206. They will be sharing their activities with us and see if we can cooperate and in their activities, or they can cooperate in our activities. And that is another direction we are moving forward. So this is, in a nutshell, the introduction of our committee. So if you have any questions, I'll be happy to answer them. Thank you very much.
Thank you. Thank you.
Any questions? No
Have any
questions?
no questions? Just God be
Okay.
with you and help you with the future.
Thank
I'll
you.
try
Thank you.
to sneak in the room 133.
Yes, please, please.
I
Yeah.
didn't promise any other TC that, but for you,
Mm.
I will try to do it as
Yeah. Thank
president.
you so much. Thank you.
It's a subject that I really like to be part of.
Mm. Yes.
Uh, yeah, are you gonna present any?
Yeah,
Yeah,
I'm going to present
part two, dynamics.
dynamics. Okay.
Yes,
So this is going to be my topic.
all yours.
So,
Yeah,
yes, thank you so much. So as you know, in 2024, we had a very big earthquake in Noto Peninsula area in Japan. So today I'm going to talk about that earthquake field investigation and subsequent analysis on liquefaction related problems due to that earthquake. So these are going to be the contents. First, I'll give you a brief overview, then the types of investigation we perform on liquefaction-induced damage, then the results and related soil structure interaction. And then I'm going to explain those interaction through FEM analysis. And finally, with some future challenges if I have time. Okay. Just let me know if I cross time, okay? Just remind me of. Yeah. Uh, First, where is Noto Peninsula? This is the map of Japan. This is where is Noto Peninsula and where the earthquake took place. And this earthquake occurred on January 1, unfortunately, on the very first day of the year. And it was at an epicentral depth of 16 kilometer, very shallow earthquake. And it was a long-lasting seismic event with very widespread, strong shaking. The Japanese intensity of 7 and moment magnitude of 7.5. There are many building collapses and liquefaction, slow failures, and most importantly, seabed upliftment. And I'm going to talk about the forensic investigation that me and my team performed immediately after the earthquake. This is the liquefaction-induced this distribution of liquefaction-induced damage. This is the epicenter, and these are the different prefectures, all surrounding prefectures. As you can see, it's a liquefaction was very widespread in spite of the epicenter is here. Uh, so immediately after the earthquake, I formed a group of investigation team, including industry and government organization. I have about 14 members in the team. We performed the investigation focusing on this town called Uchinada town, which is located about 100 kilometers from the epicenter. This is the distribution of intensity. I'm sorry, it is in Japanese, but you can see the number and guess what it means. And this town suffered a lot due to liquefaction. So our investigation covered about this much of area, about 10 kilometer long and 100 kilometer wide, this area, which in other town. Today, I'm going to focus only on Muro area, where there was widespread lateral flow and subsequent damage to the residential buildings. So the case study today I'm going to
Is it
present is, yeah,
is it along a fault line or liquefaction because
uh,
of the soil type deposit?
not along the fault line. It's because of the deposit. Yeah, I'm going to give you a brief introduction about that.
Okay.
Yeah. So the first one is the pile supported house. This house, no damage at all. As you can see, the only damage is that because of the liquefaction, there are a lot of voids inside, but the building neither tilted nor moved. It was still livable even after the earthquake. It was founded on 50 piles of length 6 meter and diameter of 60 centimeter. Uh, he's the owner of this house, so we got a lot of information from him. And right next to his house, his friend's house, which was built on the same time, but no ground improvement measures were taken. And that house moved by about 12 meters. As you can see, this is the slab. The slab and the entrance is disconnected. So this house moved due to lateral spreading. And in this area, these are the typical example of
Was this
damage.
house on a mat foundation
This spread
or
foundation, yeah.
spread footing?
Yeah, spread footing, yeah. In fact, I talked to the owner. It seems when the the company which constructed the house, they uh, advised him to go for some kind of ground improvement or pile foundation, but because of the money, he didn't go for it, and he was repenting his action when I talked to him after the earthquake. Yeah,
I
this
saw
is the
the
house.
house moved as one piece, so structurally, was it
Yeah,
sound or it was cracked inside?
stru no, structurally it was sound. No damage due to earthquake. It
So
just
just push it
moved.
back
Push it back, yeah. Push it towards the channel. This is the channel, you
or
can
buy
see.
buy the next door land
Yeah, yeah,
and
yeah.
keep it there.
Yeah. You can see this. This is almost closed.
Interesting.
This
Yeah.
this blocked. And this is his house was here on I think October, yeah. October same year when I went there. And then the house was not there at all. He just dismantled it and he decided to move somewhere else. And there's a collapse of the quay wall. And after, I think around September, October, the local authorities, they have constructed some temporary uh, sheet pile
Keep
walls,
fine.
yeah, to restrict the movement of the soil. This about that I'll come later. And we performed a 3D laser scanning and also drone survey and on photographic survey, of course, and tried to see the pre and post earthquake movement, pre and post earthquake movement. Okay. And this blue color is the one after the earthquake. As you can see, this whole water channel here, this is moved by this distance. And this is the original location of that White House. And this is the present location, I mean, after the earthquake location of the house. Again, even through this laser scanning technique, we could confirm that is about 12 meter of displacement. We performed different types of tests. I am not going to explain it to you because of the time, but just to mention them is a portable dynamic cone penetration test, PDCPT, and screwdriver sounding test. It's a kind of test developed in Japan, STS test, and piezo drive cone test, PDC, and surface wave exploration, SWE, and of course, standard penetration test.
So the
And these are, yeah.
screwdriver is
Hmm.
like the vein shear test.
Kind of venture. Yeah, we give a torque. rotational torque, and we tried
like
to
venture. Is
like a
it one
venture. Yeah.
blade that you rotate or three blades or
Uh,
four blades?
Not exactly blade actually. It's a like a this penetration test, some kind
I-
of rod. Yeah.
Is it more like a helical pile, like you're trying to rotate?
Yeah,
You'll
yeah,
have
yeah.
heat.
You can say helical pile. Yeah.
Okay.
Helical pile. Yeah. It's not yet standardized
Very,
yet,
very
but
different.
hopefully in future it will be. Then these are the locations in and around these two houses, one with a pile, other which was damaged, and we performed different combination of tests in different location depending on the necessity. And I'll just show you a few examples of the test. First, PDCPT. This one is just this was performed uh, just close to the building, which was pile supported. And this is the data we got from the owner before the construction of the house. This is the data, PDCPT data. So you can see that until 6 meter, the converted N value is quite low. That's why they went for 6 meter deep pile. And after 6 meter, this N value is more than 10. It's not going to liquefy. So the design was quite perfect from that point of view. But when you perform the same test, this was boring data, of course, but when you perform PDCPT, it was the value was quite low. The strength was reduced after the earthquake. And then again, 6 months later, we performed another test in the same location, and we could see some improvement on the strength. And that is because of probably this construction of this seawall, because the movement was restricted uh, after that. Then about Mike's first question, uh, this is the transition of topography in the area. This is the prefectural road, and this is the location of that house with the grouted piles. And this is 1968. It's they started developing this area by filling up. 1975, it was like that, and 2011, it was a well-developed residential area. So basically, it is because of the soil. It's mostly field soil. They have a sand dunes. So they cut the sand dunes and brought the sand from those cut slopes and fill the area. So this is the results from the PDC test, okay, at different location around the houses. This yellow color is the sand and the blue color is the clay. So you can see that mostly the field soil up till 7 meters were sandy soils with minimal fine contents. And we presume that this liquefaction in this Muro area occurred within a very shallow depth, about 2 to 4 meters from the ground surface. And that's why this huge lateral flow and ground deformation. This is the result of the surface wave exploration test. This is the route 8, which is the prefectural route here. This road here. And on this side of the road, the eastern side, there are a lot of liquefaction and lateral flow. On this dune side, sand dune side, there are almost no liquefaction on this area, this particular Mura area. Okay, in other areas they had some liquefaction, but not in this area. And there's a lagoon here. Originally, it was a Kahoku lagoon here, and this is the waterway side. So, and we found that the shear velocity here is below 100 meter per second. And again, this test also confirmed that this area is a reclaimed fill layer, which is represented as Fs, and N value was very low in the top layers between 0 to 1, and probably due to inadequate compaction during the land reclamation project. This widespread liquefaction took place. And based on this observation, we found one factor, very important factor. This is related to soil structure interaction, that this root 8, which you can see in this picture here. I'm sorry, I didn't use the power laser pointer. This picture here. This actually road effectively halted any lateral flow from this side towards this side. Probably because of the compaction of the road due to repeated traffic-induced vibration over many years. And that I'll show you through some numerical analysis later in the slide. Okay? Another one, very interesting observation. There's a city called Suzu City, which is very close to the epicenter. They had also widespread liquefaction. And this is the picture I took there. You can see this manhole. This is uplifted by about 1.6 meters. However, in Uchinada town, where we conducted a detailed survey, not a single manhole was uplifted. And this was quite interesting. And one of my colleagues, from the local construction company, he went there in one day and opened up this manhole and tried to see whether any ground improvement or any other measures were taken. There's no ground improvement or nothing like that in the manhole. So that means this liquefaction in this town occurred at a very shallow depth. That's why there is no upliftment of these manholes in this town. So let me explain to you through this the FEM model of the area. We constructed a conceptual geological cross section based on the boring test. We also conducted one boring test in that area, and also from different tests, PDC test and other tests and subsurface exploration test, we arrived at the geological cross section of the area. And based on that, we formed our FA model. This is the route 8. This on the lagoon side is the dune side, sand dune side. And we took the closest JMA station as which is the Tsugatamachi Kagatsume station, the closest data available. And this is the acceleration versus time earthquake record.
If we can go a bit faster.
Okay, I'm coming to the end, almost. Yeah.
Okay.
And this is the input motion. And using that input motion, we performed analysis. And also based on our previous record, we had pre and post earthquake topographic data. This is the topographic data, and these are analysis in the initial state. This black line and the red line is the final state. So you could see that there are some settlement on this side and this side, and some upliftment on this side. And this is the excess porotor pressure and shear strain. This right side is the shear strain at different time, 25, 30 to 60 and 80 seconds. This is the strong shaking, okay? Until about 80 seconds is the strong shaking. And you could see the liquefaction here. There's a red means the liquefaction because it's a excess pore water pressure 1. So you can see how the liquefaction is spreading at different time. Okay. And accordingly, the shear strain also developed within the whole area. And at 60 second, 80 second, the shear strain is almost red, means a very high strain generated within this area. So, but we could not see any lateral flow or too much deformation of this prefectural road, which again confirm that this road has prevented any flow from this side to come towards this side. So practically, because this area was having a little bit of gradient, it is not a flat area. So because of that, the lateral flow took place and induced so much damage to the structure, and many houses
From
were
the previous
damaged.
slide,
Yeah.
I saw like an uplift of 2 to 3 meters
Yes.
next to
Yes.
Route 8.
Yes.
I
Yes.
didn't see
That.
it.
Mhm.
I didn't see it in the finite element
Mm.
model.
Yeah.
Yeah,
Yeah.
here.
Yeah. There is some because this is our first analysis. Actually, we still have to improve. There are many assumptions we made in the analysis.
Yeah, I
So,
wonder how you model the Route 8
oh,
and
good question.
the finite element so that you
Uh,
stop.
yeah,
I'm
that's a
thinking
good
back
question.
analysis.
Yeah, we
I'm good,
just
Hemanta. I'm the president. I have to be good somewhere.
yeah, yeah. See, thank you. See, to answer that question, actually, we took the Japanese standard of the subsurface construction and road construction pavement
Compaction.
compaction plus the pavement, asphalt and other parts. Okay. So they
Yeah.
use some kind of drainage materials, and this is a the Japanese standard road
So
construction.
you included a
We
separate
included
soil
that.
layer there?
Yes, yes, we include separate soil layer and separate subsurface layer,
I see
separate
the
gravel
vertical line.
drainage
Yeah.
layer. Yeah, in the analysis to model the road. Yeah, that's a very good question, actually. Yeah.
If you look at TS of time 60 and 80,
Mm-hmm.
you see that there is a depression and then
Mm-hmm.
an
Yes.
uphill towards Route
Mm-hmm.
8,
Mm-hmm. Yeah, yeah,
but
yeah.
not uplift. It's like
Not uplift.
reshaping.
Yes, yes, yes. You're
So
right.
I wonder if
Actually,
the uplift is correct. I mean, it was based
mm,
on survey on ground measurement
no, not really. This is
or just
this one.
eyeing. Yeah.
Yeah, this we have
See
to
my
improve
point?
the model.
Maybe you saw
Yeah.
the delta movement, not the actual absolute movement from the area.
Yeah. And
That two, three meters is something I'm
yes,
trying to
yeah,
visualize.
yeah.
Anyways, we
And
don't want to take
another one is
a very
this the
interesting case.
thank you very much. Another one is the location of the groundwater table. We're not sure where was the groundwater table before the earthquake. After the earthquake, groundwater table actually depleted. We could confirm
It
that.
was at 8 meters, right?
Yeah, yeah, it's quite low actually. But on this side, we took the as the ground surface because we had no information in the groundwater table. This side, we also performed some tests. The groundwater level was very, very low. Yeah, about 6 to 8 meters. Again, but we are not sure. So we took the groundwater level at a shallow depth, and that may be the reason liquefaction took place in this area. But in actual observation, in our observation, there is no liquefaction in this side of the road, actually. The houses were all okay this side. So this model we still need to improve. Yeah.
Very nice.
Okay.
Conclusions?
Yeah, conclusions, I think I'll skip it so because of the time. So that's all from my side. And thank you very much for these are some future challenges. We have many challenges, including hazard maps and groundwater lowering and cost-effective ground improvement and investigation of groundwater levels. These are some of the challenges. Okay. So I'd like to acknowledge all my colleagues, my former students, and the financial support from various sources here. And these were our team members during the investigation. I'd like to acknowledge them all. Thank you very much.
Thank you. It was cold. I can see everybody's.
Yeah, it's very cold. Yeah, very cold. And that area is a very cold area in Japan. Yeah. So this year it was about 4 meters of snow, that area.
Oh,
Yeah.
Georgia, are you ready?
I am, yes. Let me just share my.
Okay, thank you so much.
The floor is yours. Welcome, Iman. Thank you so much.
Thank you.
Okay, let me get that.
Let's see in practice.
Can you see that?
Not yet. Should be coming up.
Is it there yet? Oh, wait a second. Sorry, I've not clicked the right button. There we go. Is that better?
Yep.
Yeah, perfect. Okay. Firstly, I want to say thank you for inviting me to come and present at this ITT. I really enjoyed Hemanta's presentation. I'm looking forward to the next ones as well. So to introduce myself, I'm Georgia de Sanctis. I'm the director and co-founder of North Geotechnics. My experience has been purely in design consultancy. So I've got 13 years experience working for various design consultants. And today I'm going to talk about my practical experience of soil structure interaction, things that I've been involved with in my career so far. So I'm going to talk about what does soil structure interaction mean for me in my experience, where does it play a part in projects that I get involved with, and giving 2 project examples. So I'm focusing today more on how we address the problems and the process of the design rather than the very deep technical side of things. So these examples are quite small, relatively small projects, but it was how we were trying to develop design processes that are proportionate to the project and the problem that we're addressing. So firstly, what does soil structure interaction mean in my practical experience? So it's designing a system that behaves as one. So it's rarely looking at isolated calculations. It's about looking at a system, understanding how stiffnesses, movements, and construction sequences interact across this system. We're usually looking at deflections and movements, and it requires a holistic approach to the design that usually spans across design disciplines. So it's not just a geotechnical issue, it's also working with our structural colleagues. And the examples that I'm going to show today don't include finite element analysis, which I thought was kind of an interesting side to things, given that I was sure that there would be FE analysis covered. It's what other ways can we look at these problems? So as geotechnical engineers, we're always putting structures into the ground and on top of the ground. But where is it critical to consider soil structure interaction is where the soil and the structure actually acting together, in particular with retaining walls, any propped structures and excavations, integral structures and tied and anchored structures. So today I've got 2 project examples that are quite different, where I've looked at some of these in a bit more detail. So the first example is in Bath, which is in the south of the UK. This was a new river wall, sheet-piled river wall on the River Avon. And due to soft ground and a variable groundwater and flood scenarios, meant that the wall design didn't work without some sort of anchorage. So you can see there's two parts of the wall which are anchored. So we split these into two and created two pile groups with steel tie bars as a anchorage. The groups had 750 millimeter diameter CFA piles. They were tied with steel rods. So it's quite a 3D problem with pile groups were buried and the ties were splayed at different angles. So we had to come up with a design process that could analyze the wall as well as the anchor and tie bar setup. So the design involved using Wallop software, which is a retaining wall analysis software, and doing the retaining wall. We started with this, which is in the top right of that cycle, and estimating a stiffness for the anchorage system by modelling a prop on the wall, and then looking at the forces and deflections within that prop, and then verifying the capacity of the ties, checking those.
So, yeah, are you gonna show a section view to see
No,
the different?
I don't have a section view. No, sorry, I was just
Can
talking
you go back just for my yeah, so how deep are the sheet piles?
The sheet piles were 12 meters deep.
An embedded portion below the seabed or riverbed?
The majority of that, it depended on the river level, but it was 8 meters of that was below. They got to
So you have 8 and 4.
Mm.
And the anchor steel bar, the tie bar,
Yes.
is at the surface or 2 meters below,
they were buried. They were buried about 1.5 meters below ground level. So there was a whaling beam across the back of the sheet piles that connected them all together.
And they're tied to the sheet piles by welding directly the bar to the sheet pile, or there's a whaler beam?
Yeah, there was a whaling beam, yeah, that connected them to spread the load.
Steel beam welded to all the sheet pile.
Yes, yeah, connected through.
So you install the sheet pile, you excavate, you weld the beam,
yeah,
you tie, and then you backfill.
Then you backfill over the top, yeah.
And what protects the steel tie bars with time from corrosion?
We had to take that into account. We had to take some, so they were coated, and then we had to look at long-term stiffness of the
oversizing.
Oh yeah, exactly. Yeah, allowing for some corrosion over time. Yeah.
How many millimeters per year, or per 50 years?
Oh, you're asking me a question now. I think I can't recall exactly how much.
If it's very, yeah, you should count for solid steel 1 millimeter every 20 years, maybe.
Yeah, it was quite a significant amount, considering that they
oversizing.
Yeah, of oversize.
And protection, of course.
As protection, yeah, exactly.
Sorry to interrupt, but
no, that's okay.
I really like this.
So yeah, so
I'll give you extra time.
that's okay. So we calculated the forces and resolved the forces from the ties on the pile cap. Looked at the piles individually and then the piles in a group. Applied that load to the pile group. Looked at the behaviour of the pile group overall, and then fed that back into the wall calculation, and then iterated until you're getting the same deflections out of your wall calculations, and ensuring that the structural capacity of all the elements is also acceptable. So you'll see some similarities with the next project as well, this cyclical design process. So in this case, really, the soil structure interaction was fundamental to ensuring that we had compatible behaviour under the expected loads. So I'm going to move on to the next example project, which is the A57, which is a road bypass near Manchester in the north of England. In this case, it was a bypass being built to reduce traffic where the main road was originally going through a small village. The project was geologically interesting. It had a geological fault nearby, an artesian groundwater, and there was multiple different types of structures, propped, anchored and cantilevered walls, a piled underpass and an integral bridge. I'm going to talk to you about one of the integral bridges. And for those that are interested, we wrote a paper, not particularly on the soil structure interaction, but on a practical assessment of risk for the underpass, which is just adjacent to the bridge that I'm going to talk about. So this is an architectural render of the bridge in the foreground. It's a contiguous piled abutment, and it's a fully integral bridge. So integral bridges and structures are now more and more desired by asset owners to reduce maintenance costs. However, they are more complicated for us to design. As a very simple, simplified diagram here, we had granular fill behind the piles, which can cause a strain ratcheting effect and can be critical for the design scenario of the piles. So we needed to ensure that both the structural and geotechnical models were compatible to verify this ratcheting effect. And we couldn't effectively model the soil and the bridge with all the different traffic loading scenarios in a single model. So we had two different models. You can see on the left-hand side, the geotechnical model, and which was again done in the software Wallop, where the pink arrows at the top, if I get my laser pointer, if you can see it, the pink arrows at the top were modelling the bridge as a prop and a restraint. And then on the right-hand side is a model, which is the structural model representing the bridge, and that simplified the ground with pressures and springs. So neither of these models fully captures the reality, but together they were used to model the behavior of the system as a whole. So
Quick question.
Yeah, sure.
So, and to the right, I see that the walls of the bridge in blue are contiguous piles.
Yes.
So it means this was done top down. So you put the piles, to put the plate, and then you excavate under.
Yes.
I really like that.
Yeah.
I've done the first top-down bridge like this in Lebanon.
Okay.
20 years ago.
Yeah. Yeah, because the new underpass,
very efficient.
Yeah, the new underpass is coming in at a lower level than the current existing ground level. So they're rerouting the road as it is, putting the piles in, putting the deck on the top, and then excavating. So what we had to do was ensure that these models were coherent, and we did a cycle to calibrate for a single load case. So the Wallop analysis, in line with the UK standards that dictates how you deal with traffic loading on structures, gives the envelope of earth pressure coefficient K star that should be used for limit equilibrium calculations with integral structures. So we completed that calculation in Wallop, modelling the bridge as a prop and a restraint. And then alongside this, we had the LUSAS model, where the ground is characterised with the earth pressures and springs. And we compared the responses of both of these models and iterated until we had similar deflection and moment results. So this gives a summary of the calibrated bending moment results between the two models. So the orange is the geotechnical model and the blue is the structural LUSAS model. And once these models were calibrated, then the pile design was completed in Wallop using outputs from the Lucis model for the different load cases, including expansion and contraction. So on this project, this highlighted the importance of calibrating the models to capture the system behavior, particularly where cyclic loading and strain ratcheting can govern the design. And rather than relying on a single model, we showed that practical, source structure interaction design can be achieved through iteration and comparing between geotechnical and structural analysis to give confidence in the overall response. So in my personal design experience, there hasn't been that many cases where I've need to look in this level of data at source structure interaction, but there are obviously complex cases where it needs to be checked. It's highly dependent on getting good ground investigation data to ensure that you can capture the envelope of the possible parameters of the ground behavior of the soil. It's ultimately about understanding how these systems work as one, particularly where movement and construction sequence are critical. And successful design depends on collaboration between geotechnical and structural engineers, and using engineering judgment to develop models that represent the problem without necessarily becoming overly complex for the design that's being done. And thank you very much.
Can you go back
Sure.
to your slide number 2?
Number 2, all the way back.
Yeah, this one.
Oh, wait, sorry, this one?
Sorry, not slide number 2, maybe 4.
This one?
One more.
This one?
Yes, this one.
Yes.
Suggestion
Yes.
for next time. A structure like this to carry lateral loads with a group of piles that are vertical. If you cannot make them inclined or battered or reticulated for lateral support, and here because you did them CFA, so they have to be vertical. I would, if you look at my hands, I would shift them so they are in zigzag formation.
Yes.
So
yeah.
I would shift them and keep them apart because the moment at the top will give it a better resistance for lateral support, but also so that the front pile wouldn't reduce the lateral capacity of the back pile.
Yes.
That's why I only remark.
Yeah. We were very constrained for space, as you can kind of see from some of the boundaries that we were working with.
Oh, I'm talking within the same pile cap.
Yes.
Shift them a little bit.
Yeah.
But I really like your presentation. Thank you so much.
Thanks.
Ajay, how do you pronounce your name?
Ajay is perfect, so I think we can.
Ajay,
yes.
Floor is yours.
Okay. Let me see. All right. Let me know when you can see it.
Dead man anchored retaining systems.
Perfect.
Yes.
All right. First of all, I do want to thank Marc and Hemanta for doing this and inviting me, and a special shout out to my advisor, Dr. Sanctis from A&M, who invited me. So I'll be happy to present. Then again, want to thank my colleagues in Jacobs. I've had a lot of discussions about these topics, and it's always a pleasure talking to geotechnical engineers on some of these things and how to go about doing it. These walls, as such, I kind of got into about 3 years ago. So this is kind of my experience with designing these. So just an introduction, I'm Ajay Shastri. I'm a senior geotechnical engineer here in Jacobs in the Houston office. And today I'll present on dead man anchored retaining systems.
Too young to be senior. Must be very smart.
Actually, I kind of have the same experience as Georgia. So it's about 12 years for me this year. So All right. So the agenda basically I'll just talk about anchored wall systems. A lot of what George spoke about already, but specifically I'll talk about dead man anchored systems. What are the advantages, disadvantages, and then we'll talk about your traditional approach for looking at that, and then looking at some of the more advanced analysis. And then I'll get into a couple of project examples, and then just a few tips similar to George's mine actually for design on how to go about doing this. All right, so what are anchored wall systems? Anchored wall systems are just your basic retaining walls with your added structural elements to provide better structural stability, to improve the internal stability of these walls, right? And these would basically consist of your structural tiebacks, which is basically your tie rods, cables, and in some cases even your helical piles. So basically some sort of grouted anchor or helical piles to improve your
Quick remark.
Yes.
I'm sorry today. I don't know what's wrong with me.
No, go ahead, please.
But when the wall has a footing like this,
yep,
it's rarely anchored.
Correct.
Because you have to either go a bit lower, but by the time you build that footing,
yep,
means you excavated already the top. So why
Correct.
do you want to anchor? Make a bigger wall.
So I can give you a good example for this, right? So think of it as an existing wall that you have, but now you're deepening the excavation. You're saying, okay, it's not safe. Yeah, strengthening it. Now I'm going to give you more anchors and I'm going to do it. Of course, this is an AI generated image, so you can imagine it doesn't really understand.
Ajay.
Yes.
Ajay, you won.
It can, these anchors can complement any traditional retaining wall system. So this could be your gravity walls, it could be your sheet pile walls, it could be your secant pile walls. So all of these can be complemented with a grouted anchor system like this. So what's the big advantage? You have space efficiency, which you can achieve. You can arrange your anchors so that you can achieve the kind of moments and make sure that your structural elements are not getting stressed. These can be suitable for extreme loading, so your earthquake loading, your flood loading, high retention loads, it can actually be used for that. Big advantage is observable strength, meaning once you install the anchor, you can proof load these anchors and you can see exactly how your wall is going to likely behave when you have your full load on top of it. And so that's a really good practice for our geotechnical engineering as such. In case you have temporary construction, you can always remove and reuse these anchors. So that's a big cost saving that you're getting to it. The disadvantage, yeah, go ahead.
Because this is my field of expertise. But I want to make you laugh a little bit. Disadvantages, risk to utilities, because you have utilities that are deep in the ground, and then you're drilling an anchor under infrastructure, roadways.
Yep.
But sometimes we had a case here close to me. The contractor saw a big void and he grouted it. 6 months after, it turned out to be the archive room of the hospital. And they couldn't retrieve any file from it. The nurse opened the door and she saw a big grout wall in the basement of the hospital, just to make you laugh. Keep going. So it's risk to utilities and risk to archive rooms.
Exactly. I mean, and this is why you have to do your utility survey. You need to know where your as-built drawings for all your piles are. Make sure that nothing intersects that. It's also an potential issue with corrosion. So maintenance might become an issue if you don't design for that, depending on what you're actually installing it. These grouted anchors or helical anchors generally require a specialty contractor. So if these contractors are not available at the timing or the state or the location that you're in, then that might potentially give you a problem. It's also sensitive to soil conditions. So particularly weak layer will technically give specifically at the top, will kind of give you a challenge of not being able to restrain movement and control deflections as such. It's also subject to construction sequencing, assuming you have a potentially large gap between existing grade and the fill behind. You need to make sure that the construction sequencing is perfect before you can actually go about installing these anchors. So it's a little bit of a challenge from that perspective.
Ajay, for the
Yeah.
advantages,
Yep.
you're showing reusability. You mean for the helical anchor?
No, for certain amount of grouted anchors, you can technically remove, detach, and then you can recover the material depending on what situation you have. We have a few projects which are now coming online, basically, where
You mean reuse the anchor itself
or yes,
by
or
retensioning it or removing it and reusing it?
removing it and retensioning. It depends on where it is. There are applications wherein we have seen that they've been completely removed and you're recovering the steel and recovering the part of the wall itself. But it's rare, because usually if you're trying to do it for a temporary excavation, it kind of makes sense. But for a permanent project, there's a whole lot of corrosion which should have already taken place. So it's a subjective interpretation at that point. How do you overcome this? One solution is to use dead man anchors, and dead man anchors are basically, if you think about it, it's a heavy weight which will give you a whole lot of lateral stability, or which is basically relying on lateral resistance. So ever since the dawn of civilizations and seafaring, we've been using dead man anchors to anchor our ship. So the same concept of this is now for the retaining walls. And this could again be anything like a large concrete block. You can have sheet piles, you can have drill shafts, driven piles. You have a variety of the thing, and it can complement other retaining walls. And this is the interesting part. Traditional deadman anchors are basically your log piles, as shown at the bottom figure there. And there is a history of ground anchor piles, which I was going through when I was preparing this presentation. And the entire thing was deadman anchors were created, like the analysis part, in 1912. So the technology is like 100 years old, right? But that article itself is very interesting, because it talks about grouted anchors and helical piles in the 19th century, and it's by this blind Irishman. So you can take what you will with that thing, but it's a very interesting design process that we have evolved over such a long period. All right, so what are the advantages? So assume you want to control your displacement at the very top and you don't have favorable soil conditions. This will kind of give you an option to do that, because you'll be able to adjust the height of your anchor such that it'll be able to you'll be able to calculate exactly what's happening. It doesn't require an anchoring strata, because it's mostly using your lateral resistance, the development of a lateral resistance. So in case you need to do it, you can always go deeper. You can install a different kind of a dead man to basically supplement your resistances. And this can be installed at different height. You can install it from anywhere between medium stiff to stiff soils. You can go into rocks if required, but generally then you would look at a grouted anchor at that stage. The big advantage, at least the way I'm thinking of it, is it doesn't require a specialty contractor. Your dead man, because of the traditional dead man that you can generate, you can use number of conventional conventional contractor, and a normal foundation contractor would be able to install half these things that we are talking about. So it becomes a little more advantageous when it comes to the actual construction side of it. How do you go about analyzing it? You can look at a traditional limit equilibrium analysis, and there are specific guidelines provided in all these documents. The Caltrans model, the Caltrans document, which is the newest edition, which came out last August, is the latest thing. It's just probably actually giving you the most detailed amount of information for the design of these anchors. And basically what it relies upon is that you're assuming most of these structures are rigid, and then you would estimate a point of zero moment, and then you would space out your elements such that your active and passive edges between the retaining wall and the anchors don't overlap too much. Then you would perform a limit equilibrium analysis, assuming things are rigid. What that would generally do is it will make your forces higher on your members, but then your displacements are zero, right? And therein lies your potential hassle, because nothing in the world is perfectly rigid, and that creates a problem. So that's when you might have to switch to something like an advanced analysis. When displacement is a concern, you want to measure exactly how much it is, and you want to control that part of it. Or let's assume you have to do it in stages. You want to simulate construction stages as you're putting in fill, you're excavating, there are scour conditions. You would want to then say, okay, what is going to happen on a step-by-step process? So as Georgia, I know she didn't cover it, but Finite Elements is a good alternative for this. And there are a number of commercial software out there like DeepX or Plaxis, which can do this part for you. Special shout out to the model that we've been using. I work primarily in this region, so which is basically Texas, Florida, wherein we have soft soils as well as hard soils. So effects of consolidation, effects of compressibility can be modeled with this model. This is usually a Plaxis model, but I think RS Pile also has a similar setup. Essentially, if you think about what the soft soil model is the Moore-Coulomb model with a cap for the P side, which is the mean stress side, and they're excellent for capturing your nonlinear pressure dependent stiffnesses. Does require a little bit of calibration depending on the soil. So getting the soil data, getting the lab tests correctly is important for this entire mechanism. I'm going to move on to a couple of project examples. So this is a port site in Texas. The picture is of an existing one close to the site, but not exactly this one. Our project has gone from now it's 100%, and the contractor is just about constructing it right now. What it involves is we have a retaining wall about 1,200 feet, and I do apologize. We work in Imperial. it's no SI units. I need to convert everything in my head and tell you, but it's about 1,200 feet. The retention wall, which is basically this one, basically is your consists of 36-inch drill shafts.
You multiply by 0.3048.
Correct.
Or divide by 3.
Correct. 36-inch drill shafts. They're spaced at 45 inches apart.
Like
and the way you're doing it is that you're jet grouting in between. Your deadman anchor is an NZ 14 sheet pile, and
so the goal is to bring bigger ships.
The goal is to bring bigger
dredging,
ships.
Right?
You're dredging, but there's potential scour at the end. So you're dredging a part of the port. You're building that anchoring system that you see here. You're putting it on top. So there'll be a dock which will be placed there, right? So all of that is happening.
Deadman is close to the containers.
Your deadman is closer to the containers. Yes, it's actually, it ends before the containers start. So it's somewhere here. So this is a fair bit distance away, but not at the container limit yet. The mooring, there's going to be this mooring dock, which is going to be put in front of the retention system. And the initial height after construction is about 20 feet. And then when it finally scars, our design condition is more like 30 feet of this thing. But when you look at it, when you look at it, because of the slope, you're actually looking at a potential 70 feet difference between the top of the height to the bottom, right? Stratigraphy here consisted of structural fills, soft clays underlain by sands, and then you get into over-consolidated clays, which is kind of your this thing. We did an undrained analysis during construction and a drained analysis for post-construction to develop the design envelopes. Initially, when it was going, when it was conceptualized, and then when we moved into 60%, we were looking at a PY wall, which is a PY wall analysis to design the retaining wall systems and then develop the maximum bending moments. And then we used an L pile to kind of simulate what was happening with the deck and how that's happening. The spring stiffnesses from those software were input into STAT, and that was used for your structural design. But because the construction sequencing and the various structural elements which are coming into play, we wanted to get more of a holistic model. And that's when we brought in Plaxis, and then we used the soft soil model to simulate the entire model with the construction sequence. Second example, slightly different application, but a similar concept that we are using. So this is a river pump station that we are doing in North Texas. The pump station is going to be located right almost in the middle of the river. They have what is called as a wet well concept. So you'll excavate into the bottom of the river and then put the pump at the bottom of that. So to protect this pump station, you have these two wing walls on either side, spanning about 500 feet. Maximum height at the end of construction is about 60 feet. And then because this river erodes and scars continuously, or we are anticipating a lot of scar, we are looking at potentially 90 feet of retention at the end of this thing. And for this, we did want to try to make grouted anchors work, because we have over-consolidated clay, sands, and then weathered shale. So those are good anchoring strata, but it's just some locations became so far that the anchored walls wouldn't work. We tried various combinations, and we said, okay, we'll probably have to switch to dead man anchors for this. And that's when it started to make a whole lot more sense. The graphic here is a little outdated because we ended up moving the top anchor right up to the back, and that's what actually got us to a workable system. This is still under design. This is going to 90% design starting next week. Actually, we'll start up the 90% design.
And the advantage of dead man anchor, another advantage, you can install it from the backside if you don't have access from
the front.
You cannot put an anchor here, stand up in the river.
Exactly. And I mean, these
design.
These are technically combi walls, so which is basically steel pipe piles interlaced with sheet piles. So it's a very stiff retaining wall system. But even with this, it's you cannot work with any other anchor.
What's the height?
90 feet.
60 feet?
60 feet for post-construction, 90 feet is our design condition once it's scars.
Height for design after scar.
And we have flood conditions we have to design for. We have to design for drought conditions. So if the water in front of it disappears, then
drawdown.
Yes, exactly. So there is a lot of things to consider, a lot of design conditions which are occurring here. So was a more challenging design as such, but we kind of got it to work right now. We did a bunch of limit equilibrium analysis using MathCAD sheets.
Yeah, 5 minutes.
And Dr. Ballouz, I remember when you had presented at A&M, I remember you bringing this room-long differential equation to solve it. So we have an engineer, senior engineer.
Oh my gosh.
You have a senior engineer who does that similarly with his MathCAD sheet. So he has like a 10, 15-page MathCAD sheet, which does that.
I wish there was MathCAD then. When I did my PhD.
We used STAT for our structural design, similar to the other project, but then we did finite elements with Plaxis to model the entire construction sequence. That kind of helped us do the thing. So we are doing more refined analysis as we are going to the 90% design, and we'll finish it before the end of the year. Last slide. So best practices is to plan your investigation. So my slide is probably a copy of George's. So it's essentially plan your investigation properly. All these things are highly dependent on how basically variable your soil properties are. So you need to characterize that. So you need to plan it properly, collect your samples appropriately. Our shale here was very difficult to sample. So we had to use slightly inventive methods to, I wouldn't say inventive, actually, I would say more non-conventional to the location that we are looking at to get the samples out, perform the appropriate type and number of laboratory tests. For some of your soft soil models, the calibration is a little difficult, so you need to make sure that you have the right tests. You have to have enough Atterbergs, you need to have your UUs, CUs, all of that in line before doing it, so plan for that accordingly. Understand your project design requirements, meaning there could be pipe piles might not be available because there's a steel shortage, or your contractor might not be knowledgeable about how to install a driven pile over a drill shaft. So all those things come into play. switch to an advanced analysis as required. These are conditions which require you to switch to a finite element analysis. Others, you might be able to get away with doing a limit equilibrium analysis, so you only need to switch it as required. And as George was saying, coordinate with your other disciplines. We are on the resistance side, they're on the demand side, so they understand certain aspects of how the structure is actually going to interact with the soil. So you need to make sure that you're interacting with your structural leads, with your H&H, hydraulic folks, all of that, to understand what their requirements are. I'll close out with this statement. Everything should be made as simple as possible, but not any simpler, by Albert Einstein. So, that's my big takeaway from all of this. So,
the great Albert. Thank you,
Yeah.
Ajay. Go back a couple of slides. Yeah, this one. So if you zoom on the picture,
Let me try.
yeah, you see that the curve is open like this.
Yeah.
Imagine that the push is from the other river side.
Yep.
And the river is on the inside side. It's safer. In other words, you'll have some arching. So what I'm gonna recommend to you is be careful with 2D analysis.
Yep.
Even if it's a wide circle, you have to put extra safety.
Yep.
Because the closer, the higher the risk in 3D. Or
Correct.
use Plaxis 3D.
Correct.
I should be paid by Plaxis now.
No, this was an interesting case study. We thought, why do you have to do all these wing walls? Why can't you just install it here? We'll design retaining walls just around the wet well. But the client's concern was because of the nature of the river, it brings in a lot of debris. So they had to have these wing walls to protect the pump station from the debris, which might flow underneath it, and to clear it, it was a big challenge. So they said the only way they can protect that entire area is to build the swing wall. And that suddenly now started bringing up a whole host of challenges, because the slope of this thing goes from here all the way down and then comes. So you're putting all this fill right back there. So
one story for you, for all of you. Opeyemi, you know where's Ondo State? Prepare your slides, but you know where's Ondo? In Nigeria?
Oh.
Yeah, you are muted. So in Ondo State, there was a bridge, and they called me that the abutment is on 50-meter piles, 20 piles, 1 meter diameter.
Okay.
And they when they backfilled it 8-meter high to take off on the bridge, the whole thing moved laterally 2 meters. And I used dead man anchors with pre-stressed cables to bring it back to its place. Not 2 meters. You should never go back to maybe 1.5, the elastic portion of the pile deformation. So we used dead man anchor like 100 meter far. That's why when you said you pushed back the dead man anchor, and the picture you're showing, you said 2 dead man anchor on top of each other. I didn't like it, but then you corrected by saying you pushed back the top one because they don't want them to interfere.
Correct.
Yeah.
I love it. Opeyemi, the floor is yours. Thank you, Ajay.
Of course. Thank you.
It's taking more time but I like it. I told you I belong with your committee, Hemanta. You're muted, Hemanta.
I'm sorry. Yeah, you should. You should come to our committee.
After the presidency.
Yeah. Why don't you
4
join?
more years on the board, maybe after 4 years.
Okay. But you can still be an advisor.
You're my advisor.
No, not at all.
Please,
Okay.
can you have my screen now?
Please.
Yeah, you're good. You're good.
Thank you very much, Mr. President. I want to appreciate this privilege I have whichever way it goes with me today, I have a cover. Mr. President is going to cover me. I hope that anytime soon I cover Mr. President, a Nigerian citizen. So I am covered by him. He's been visiting us over the times, a consultant, one of the leading geotechnical engineering firm in Nigeria. And I'll be speaking to you about chemical alterations of soil properties in municipal dump sites. I am still a PhD student.
Did you go with us to the technical tour in Eco Atlantic project?
Say again?
The technical tour. Did you go on the technical tour we did with the
No,
conference?
I returned back to my university after the second day of the technical section
Okay.
because that was just a meeting I have to attend to bring my student because some of my students came with me to the conference. In fact, you have them here. So they have to
Yes,
return
yes.
on exams at the university. So I wasn't able to go with
Great
them.
students.
Yeah. So thank you, Mr. President. This is my first time of meeting with you at the African Young Technical Engineers. That's last month at the University of Lagos in Nigeria, and I'll be speaking. So whichever way it goes, as I said, Mr. President have my back. Is used to Nigeria. He knows most of the things happening here. And so I'll be bringing my own submission to what the leading professors and experts in the industry has presented. So this is worth talking about, this interaction of soils and in relation to our retaining works and the like. So my own part of it I'm sharing today is part of my experience I've gained while I was having some research work related to municipal dumping sites in Oshogbo. Oshogbo is like about 3.5 hours to Lagos, where Mr. President is used to. And this this city it generates what's bring my interest is that it generates a lot of municipal dump sites, and it's a fast-growing urban area that now that after over the time that we need more lands, to accommodate people that's coming from other states, other parts of the country to settle down in the state, and so the city is becoming wider by time, and then the land area that is available is no longer enough to build houses to accommodate them. So what happens presently is that they now started moving towards some of the suburbs, some of the areas that are outskirts the town in the city. And those areas before are used to, their legacy dump sites here and there all over the places. And so what prompts my interest is to have this research, to go into this area and then find out what has happened over the time. It was interesting to find out some of these, legacy dump sites have been there for some for 15 years, some for 10 years, some for 20 years. And I wanted to find out what impact would this process of dumping has had over the interactions of soil, and then the relation to that of what is going to happen in case a retaining wall is going to be situated in those areas. So I have this. So cities have been built and, they rebuilt over the time, I said, but over the ground that we can no longer trust because there are some processes that have happened over the time, the dumping processes, the breaking down of the manner. So that was what interested me to put attention into this area. So what I did was I located 5 different dumping sites where, dumping process have been going there over the time. And then I picked 5 of them, and then pick some other 5 area where there was no undisturbed contact, that's about 30 to 50 meters away from those areas where there's dumping processes. So I wanted to check in comparison to a control samples of what is happening in that area. So my findings, of course, I did what we did over that period was I did some characterizations of the index and the geotechnical properties. And then aside of the dumping site and the uncontrolled area where there was no dumping processes, to be able to relate and compare what is happening to the reactions that has happened in the soil over the time through to that process, and then what I can do in comparison to those areas where there was no dumping processes. So to quantify and to find out what exactly or some of those parameters have been highly influenced such that I can now make decisions on it in case I want to do design or foundations or retaining walls. I have to use R to do ANOVA, that's analysis of variance. I did that using R, that's programming language in R Studio. And then that was not able to make some, from informations that can now present to the government of the state, such that it can guide the movement of people towards those areas as people were moving. Of course, This is in relation to, is in alignment with the United Nations Sustainable Goals of Good Health. Of course, the part of the pollution, and then the part of the sustainabilities of the cities, and then the sustainabilities of the processes and the safety of what is happening within the area as we have people moving to the state. So these are the things that guided my my little research that I did in those areas. So for the study area, as I said, this Osogbo is the state capital of Osun State. Osun State is one of the states in the southwest Nigeria. And if you look toward this area, this is the this area. So this Okini side, this Ibokun side, this other area are the area when the city is getting full. So people are moving towards the end of the cities, and these are the places where those dumping sites have been located. In fact, in my next slide, you have these processes ongoing. So you have this. I have these samples representing the solid waste dumping site. Of course, it contains a lot of debris, the fruiting, the plastics. There's so many of these, coming from these different angles of the town of the city that are taken towards those ends of the city. Now, so in fact, this is what I have for this 5 legacy dumping site. This area, you can see that for number one, this my thing does not really capture because these locations are actually tending towards the edges of the city, because that is where people are moving into now, because within the city now is getting full. So for number one, the first location I have was about 15 years, because I have to make interactions with people in the area, the histories of the dumping site, the time it has been used, and then I could see it physically. And so I have those 5 locations that I use as dumping sites, and then I have to go for each of these locations. I have to go about 30 to 50 meters away, then to take samples also from those areas, and then all of this analysis, the index property analysis in the laboratory, the geotechnical property analysis. I did a fit test, which is that of the CPT. I also use CPT.
Why don't you go a bit faster? We're good.
Okay. So I did CPT, all of these tests to find out, and I have all this, soil classification standard to justify what I did. So for the findings, these are some of the findings I have that is now informed. So for index property, that the soil is no longer itself. So the dumping processes that have been going on over the years has actually affected the soil. For example, the natural moisture content. You have the dumping site, which are in this pink, and then the control samples, which are places where there was no dumping operations. The dumping processes are this black. So if you look at it, you can see that the differences is very clear. For example, in that location, sample location 3, you can see how the soil moisture content at a particular where there was dumping site, and then compare to the area where there was no dumping location. Then for the liquid limit, as part of Patagon limit test, you have that
Opeyemi, are these dump sites similar in terms of the way it's
in terms
used,
of the
like
way,
they dump and push, or are they compacted, or
no, they were not compacted. They were not compacted these mechanical means, but the dumping processes over the time, when you keep adding something over and over again over the years, there's a way that that will be this overburden will naturally be adding up and piling up, and then having some levels of compaction by itself, not by any mechanical means.
so natural moisture content at which elevation?
The
At
moisture
which level?
the moisture content at the depth, I have a CPT, did a CPT test. So the depth were varies. That's part of the findings. The depth at which I have to reach on those dumping sites, the depth at which I have to reach soil where I could take samples on were very far away from the surface because of that dumping processes over the years.
So how deep is this natural moisture content percent number?
Some of them. Yeah, some of
It's
them.
an average?
Yeah, I have. I guess the some of these slides still speak to that slides over, because I have some slides that still speak about those depths.
Okay.
Especially when I was having yes. So for then the gradations, I observe also the gradation, the leachate break down the soil skeleton part. So the control area were well graded. those areas where there was no, dumping processes over the time, but those areas, the dumping site itself, you see that the soil, the gradations have become graded, so have become gap graded. So even though some of them were showing symptoms as if they were going to increase in strength, but when you now check the gradations when I put into, the particle size analysis test, then you observe that they become gap graded. So for the controlled area where there was no, when there was no dumping activities, you have them that are well graded. Of course, you have the acetal classification. I have A1, A16, I have A1B, and then A1B and A1A. But when you now move to the same locations, that's about 50 meters away now, you now have from A1A is now going to A26, that become gap graded, and then it's no longer fit, because basically in Nigeria, we designed a road based on using this ISO standard, and then CBR and some other factors that were put in place for the design processes of road in Nigeria. So for the area, the soil sample that are now in the area where there is dumping processes have become gap graded, which means they can no longer be fit for use of highway. Then for strength, that's on the geotechnical properties now. So somehow the strength is up, but not for a good reason, of course. So the MDD, the CBR, and the sand strength are higher over the dump site, but the gradations is poor. Those are the dynamics of the thing that started making me to, have a second think and a rethink and check over again. Because initially I was thinking that because of that processes, the chemical processes, the leachate was going to reduce the strength, but somehow the MDD, at some of those sites have, as you can see, this for this sample location 1, you can see that at the dump site, the strength, the CBR increases at sample location 1 as compared to the control area. Then in sample location 4, you can see some of those things. So some of those locations improve in CBR, but of course, it's not going to be for the good reasons. In fact, the fact that the gradation is now poor has make it not fit for design, for use in road constructions in Nigeria, as I say. So in 3 of the 5 sites, you have the higher CBR, but governed by cementations, not gradations, actually. So that's part of the observations I have. Then for the shear strength, I think I need to move to now. This is the depth. Now I had this feed test, which is the CPT for dump site that index significantly greater embedment. Now for the depth, if you look at this depth for example, for sample location 1, for me to be able to reach an average bearing pressure of about 209, that's kilonewton per meter square. Now for sample location 1 at the place, I have to go as deep as 1.5 for me to be able to reach that depth. But for uncontrolled place, I was at just 1.2 meter. But look at that sample 4, the sample location 4. I have to go as low as 3.3 meters in depth. Why the uncontrolled, the places where there was no dumping processes, I only have 0.8 meter to reach that kind of a depth. So that implies that in foundation designs, the basis of foundations of structures or buildings, this is already saying that in places where you can use shallow foundation, which is mostly the case in this part of the country because, of the soil area and the bearing capacity. But in cases where there is these dumping processes, that breaks down the strength of the soil, and then it means you have to go more deeper, possibly because you have to be going into raft footings and the likes. Of course, that also is going to probably the cost of the project also start increasing. So these are some of the findings. So in the chemical part of it, because I was looking at that area, the chemical part of it, look at what actually the chemical pathway, what has happened in the area where there was dumping processes. So as I was saying the other time, the overburden, which it happens to be, the strength that will be developed of compaction of putting, compiling, and piling up of the dumping processes over the years, have a way of, internal building up over. So that will increase the compassion, as increased as a way of compacting, self-compassion. So in that area, so somehow that might be responsible for the reasons why some of the locations have, increase of CBR, and then part of them have instead of MDD. Then because the field is not of the same source, saying you have heterogeneous field, and so they're not going to behave and react the same way with the particles of the soil when they were being broken, when they're going to break down. Then the infiltration reduces are observed at the moisture content, which were asking a question about the other time. So some of them at this depth, depth of 1.2 meter, some of them depth of 2 meters. They were taken based on what that CPT, because in the the raw data was not having it. The raw data of the CPT was had to be going along the depth, and you are monitoring the depth at which you reach the water table level before you can now take the samples and check. So the densities in some cases, in some of those locations that I showed before, were increasing, and then the MDD becomes more variable. Some were having on the increasing side, while some are having lower the others. And then for the chemical processes, of course, you have there is acidogenesis condition whereby you have this glucose breaking down into acetic acid, and then you have carbon dioxide and then nitrogen gas being generated. Then that's for acidogenesis, of course, that will affect the pH values, because a decrease in pH will alter the chemical environment of the soil, and then it affects the mineral stabilities of the soil. So those are the things. Then there's mineral breakdown, of course. There's mineral weathering, because at the carbon dioxide, having a mixture with the water when during the rain over the time, and then is now forming the carbonic acid, which in turn will attack the soil minerals. It will accelerate breaking down of the soil. It changes the chemical compositions of the soil, and no wonder the soil behaviors, are now no longer the same as it used to be. So just because of time, and then the specific gravity was shifting, the outer bag limit was affected, the cohesion was affected. And then what's the implications of this for foundation, the change of foundations and retaining walls? Now, if you look at this one for the superstructure that is going to come on this basis, say for example, you have a dump site municipal solid waste here, it means that the implication for those of us in this part of the country, in those areas, those that are moving towards those areas, the implication is that it means that they have to go more deeper before they can have a native stratum that can be able to hold the structures. Because basically in this part of the country, because of the location, unlike where Mr. President is used to in Lagos, we're used to, because of the nature of the soil, shallow foundations most of the time, except you have route for some of the high-rising buildings. But in this case, I think you have to go more deeper, and then before you can, then for retaining walls, because the soil is not only, just a natural thing now. There were chemical processes, there were biological processes, there were, nitrogenesis, there is, ammonifications and all the like that is happening. So I believe in this one now, so when the retaining wall is to be designed, it's just an awareness that when the retaining wall is going to be designed in this area, for the active and the passive pressure determinations, so have to take care of all of these processes that is going to be happening, because not only going to be the condition that you have for the natural soil where there was no dumping processes, that you're still going to have in the area where you have dumping processes. So conclusively, just because of time, decades of the mineral solids waste decomposition has measurably altered both the index property and then the geotechnical properties have been affected. I have that for an MDD and the CBR and the shear strength tend to go higher over the dump site, but of course it reflects a cementation process and not as a result of not as a result of degradations. So for that alone is already sending a signal that people, when we now have most of the people coming in, the government, because the land is not becoming choking, the city is becoming choking, and people are moving towards the suburb of the state. So this has to be bear in mind, of which I've had a provision. I've had an opportunity at a conference organized at the Osun State University, where we have some experts from the Ministry of Works who are in charge of building plannings and then road constructions in the state, where I presented this. So basically, I've made these recommendations, to the government officials. I've made these recommendations. I have to present this not too long ago now at that conference, such that it becomes a kind of awareness to the government. I know that when we're having these practices, some of this area, these are the things that should be bear in mind when you are moving towards it. So I have some few references here, and then thanks to Mr. President generosity who brought in myself and some of my students from the university in Nigeria. I think we came on free of charge, and Mr. President deserves a kudos there. So thank you very much for having me. I have the acknowledgement of the State Ministry of Works, because I did it here. The State Ministry, the research work, both the field work and the laboratory work I did at the Ministry of Works here in Nigeria. Special thanks to TC207 of ITT and then the ITT moderation team. I am still myself a PhD student, and then learning to start teaching at the university. Thank you. Gracias, Eshe. Thank you.
Gracias.
Thank
Opeyemi, thank you, thank you. I hope that our children will not have to use your research to build their houses. We should start reversing the process of ruining our nature. When I see those pictures of the dump sites, it's scary. Recycle, reuse. All right. Thank you all. I think we took more time than usual, but it was exciting. I don't know if you have any concluding remarks. Thank you all, and we should publish this lecture in the coming few days. You will see it on LinkedIn, our social media, and the website. Any remark before I say goodbye?
No, just to say thanks. They were really interesting talks. Thanks, everybody.
Thank you.
Georgia.
Yeah, thank you for having me.
Ajay, Hemanta. Always good to see you, and hope to see you all in Vienna in 2 weeks.
Thank you.
Thanks.